Hello, in this video we'll cover section 2b, which will certainly continue with our basic work with units and will just be a slight extension on how we could see a lot of the unit and conversion work can be just extended into a lot of helpful situations that we do see in our regular life. So just before I jump into that, just a couple of quick points. The 2A and the 2B homework, this is what we're getting through today. These are the two eligible homeworks that we still have. As we're approaching spring break, several of you have discussed this. This is a good opportunity to maybe either catch up, get some homework done, if not finish your remaining homework assignments. So these would be the two that you should be focusing on. One very quick thing on 2A. The very, very last problem involves a lot of discussion on Kobe Bryant and his salary. I looked at it again. I don't like part C. So for that problem, parts A and B I would expect you to do, but you can skip part C. And then for 2B, this will be the homework that goes with this unit. Just a little bit more on our schedule. We have spring break next week, so again, a good opportunity to just kind of get some more practice with units, working through the homework. When we come back, Monday the 25th, I'm going to introduce a lab that goes right along with everything we're doing here, and that will be something that you will do as a take-home. And then most of that Monday will be review. Section 2C is going to be really, really fast. It's just a few points that we're going to make in class, but there's not going to be any extra homework problems. So this is where your material will end for test number 2. And we will likely have that the second Monday after we come back, which I believe that would be May 2nd. May 2nd looks like our test that'll cover Chapter 2 material. So just to give you that little sense of schedule. So now as we start to get to work, we pointed this quickly out in class, that now as we're getting more accustomed to problem solving in units, that there are a couple of things we should do. We're getting some wordy problems. They're not too long, but as we're getting some more wordier problems, it is helpful to identify the units in the problem. That when we go through, we'll see units along the way, and that we should be able to formulate ideas on what those units are telling us. And on the second part, once we have those units, to have some expectation on what the units are for our final answer. That can really help guide our work. And then step 3, as we go through and do those calculations, those computations, embrace the units along the way and make sure all the good things that were supposed to happen did happen. That the units we wanted to cancel, maybe they did cancel, that we're getting the units that we expected. So this is a very, very rough outline to try and help us. And now, I'm going to point out there are a lot of good examples in the book, but I'm going to do separate examples. So right off the bat, they give us a little problem with distance, time, and speed. We've done a few of these to this point, but even just quickly going through this, the question here is talking about how fast is it going, a question of speed. Well, if we think about something like that, units for speed. Well, we see the car traveling in miles. Our units of time are coming up as hours, so that it would be logical that we would have speed as miles per hour. Well, that tells us what to do. If the units are miles per hour, take the original quantity that was measured in miles, divide by the quantity that was measured in hours. They give us a little reminder here, dividing a fraction is multiplying by the reciprocal. But in the end, miles per hour are the final units. So that can help. We've got a formula, and some people might think about solving that formula, but just having the basic understanding of the units can really, really help out. So now I want to do several problems to go along with this. So in general, we've pointed out that the distance equals rate times time formula can almost be expanded a little bit in the sense of total equals rate times time. Here specifically, the rate would be measuring speed, but we can get similar aspects with the idea of rate. The idea of rate always has that per aspect to it. So in something like speed, we see something like feet per second or miles per hour, but other rates, we'll talk about things like filling a bucket, and we could talk about things like gallons per minute. Or, down here, we're going to do a quick reminder of the hot tub problem that we started in class the other day. And this should be understood as a rate, cubic feet per minute. But it's not just that. Think about how you're paid, your pay rate. A lot of us get paid in something like dollars per hour. Some of us have an annual salary, but for a lot of people, they work at that hourly rate. It doesn't always have to be an aspect of time. That when you purchase items, sometimes you get a price, like something like, 5 apples cost $1. So we could figure out a rate of how many dollars per apple. So there are a lot of these situations where the idea of rates come up. And in some way we can use this equation, but very often just understanding the units will really help to guide us. When to multiply, when to divide. And like we just saw on this first page, thinking about the original units, having expectation for the answer units, and then literally seeing those units working out. So let's do a few of them. Let's get our hands dirty and see how this works. So in this first problem, you're walking at 2.5 feet per second. How far have you gone in 15 seconds? I'm going to add a second part to this. This came up in class, and we did this a little fast at the end of class on Monday, so I want to take an extra moment to talk about this one. But for right now, just looking at the top. You walk 2.5 feet per second. How far have you gone in 15 seconds? How far have you gone? We're talking about a distance. What's a unit of distance in this problem? Well, here, this hopefully through the units we're identifying as a rate, as a speed, and we have feet as a part of that computation. So feet will be the units that we get for our distance. My time units here are in seconds. This is also measured in seconds, so everything matches. So this, if we're thinking about this formula, becomes a simple plug-in, 2.5 feet per second times 15 seconds. Seconds cancel. I do my arithmetic, and I would get we walked a total of 37.5 feet. And I know we were joking about this a little bit in Monday's class, but I have to emphasize it so strongly. Units, especially in this section, the units are just as important as the answer itself. So it's easy to just kind of think, okay, multiply, and sometimes you randomly guess, multiply, divide, etc. You might get lucky sometimes, but showing the work and including the units, that's what we're looking for. That's the process that we're hoping to get better at through this section. So that's all there is to problem number 1. Problem number 2 here, now again, not this problem number 2, just replacing this. Now just thinking how far have you gone in 2 minutes, there's 2 options here. The issue that comes up now is that up here, we saw how the time aspect was given in seconds. Here, the time aspect is given in minutes. So if we just try to do the same type of computation, we'd have 2.5 feet per second times 2 minutes, but this should be a big warning that things aren't working. This is what we're saying. Have that expectation for my units and then make sure it actually happens. So here I multiplied, it made sense by the formula, and it made sense by the units so that we're finished with units feet as we said in the beginning. But if I did this arithmetic, well, 2.5 times 2 is 5, but nothing good happens with the units. So that should be a clear sign to us that something's wrong. What's wrong? My units don't match. I need to have matching units here. So what can I do? In class, and I think this is what most people would prefer, they're going to look at this basic unit of time and convert it from minutes to seconds. So let me just do that on the side here. We have 1 minute equals 60 seconds. So my total of 2 minutes, the conversion factor, I need minutes to cancel, so that'll go on the bottom. Therefore, seconds go on top. Numerically, 60 has to go with seconds and 1 with minute. Minutes would cancel, and we would end up 2 times 60 is 120, specifically 120 seconds. Now we're back on track like we were in part A. And now we could do that same thing, 2.5 feet per second times 120 seconds. Good things happen. 2.5 times 120. And we would get a total of 300 feet traveled. So this is very similar to the problem that we did finish on class on Monday, but a couple of years we were walking out, there's an alternative solution. The other alternative is, this is in terms of minutes, leave this one alone, do the conversion here. I think most of us are going to be much better doing the conversion here, but to realize this can work too. You have 2.5 feet per second, but to realize I need the seconds to cancel, I need minutes, and this is in the denominator. So now, in order to get seconds to cancel, seconds has to go in the numerator, minutes in the denominator. That'll get the seconds to cancel, and my units at the end, this is still here, this is still here. That'll give me feet per minute. But again, filling in the numerical values, 60 seconds for 1 minute. I get 2.5 times 60 is 150 units. That would be feet per minute. And now my work looks very, very different here. This conversion led to this answer. This conversion, now it would go D equals 150 feet per minute. But now I'm leaving this alone, so I would just multiply by 2 minutes. So again, the work along the way looks very different, but at the end, here seconds cancel with seconds. We did the arithmetic and got 300, and the units were feet. Here, minutes would cancel with minutes. The arithmetic, 150 times 2 is 300, and my remaining unit are still feet. So we have some minor alternatives, but either way, there was conversions involved, and either conversion relied on going from either this seconds to minute or this minutes to seconds relied on this conversion factor. Okay, so first problem, we saw the rate, we were given the time, we did the straightforward multiplication to get the time aspects to cancel, left with our distance units. But now, number 2, changing up the question. Now we're traveling 165 miles in 3 hours. What is your average speed? So the 2 alternatives, thinking about the formula, we're being told the distance in miles. We're being given a time in hours. So my speed is going to be measured in miles per hour. Well, that would tell me, take the miles traveled, divide by the time. Nothing cancels here, and that would end up numerically 165 divided by 3 is 55. And units, miles divided by hours, gives us the expected miles per hour. So that's purely understanding the units. If you're more of a formula person, that's fine too. Just to realize the formula will tell me to do this. I would have 165 miles. I don't know R. I have T is 3 hours. Algebraically, how do you solve for R? This is R times 3 hours. You would divide the 3 hours, and notice that's exactly what we have. We would just end up with R equals this, but still all the work is exactly the same. So now let's try and move to this next part. Distance is a great example of this, but so many other areas that with still some aspect of total equals rate times time. So now these next couple, let's talk about filling a bucket, right? Well, here we're going to fill a bucket. Here we're going to fill a bathtub. But we're doing similar things, but the nature of the question, what we're asking is slightly different. In number 3, you fill a 5-gallon bucket in 4 minutes. At what rate are you filling the bucket? This question is almost the exact same thing as this question. The only difference is this idea of rate, well, when we talk about traveling, we already have a word for that. We call it speed. But that's exactly what we're looking for here. Here we have the total distance traveled, total time spent. We divided that to get the rate of speed. Here, the same idea. How are we going to get the rate we're filling the bucket? We're going to take how much we filled over how long we spent filling it. So 5 gallons over 4 minutes. Expectations on the units. What kind of a rate are we looking at here? Well, if this is measured in gallons and this is measured in minutes, we'd expect gallons per minute, and that's exactly what we'd get here. And computationally, just the arithmetic, 5 divided by 4, we are filling at a rate of 1.25 gallons per minute. Same exact idea, everyone. This first way, I did it thinking about the units. I could have thought about this. I know the total is 5 gallons. I know the time is 4 minutes. So same thing, same idea as we saw here. 5 gallons equals R times 4 minutes. You divide the 4 minutes over, and we're right back where we were a moment ago. Same setup, same units, same final numerical answer. But now, a little bit of a flip, okay? And notice, I'm now doing the third option. There's 3 variables here. We had the rate and the time, we looked for distance. We had the distance and the time, we looked for speed. I could have also done the distance and the speed and asked you how long we were going. That's the idea we're seeing here, right? I'm looking at, I know that I'm filled a 50-gallon. That's how big my bathtub is. I know the rate. The question is, how long does it take? That's a question of time. So there's my time unit. This is where I think we should have at least some good sense with the formula. You know, this is where people just do what they want. Some people just want to do 50 divided by 2, but other times they want to do 50 times 2. Well, which units are going to make this work? We need minutes for my final answer, but the fact that minutes are in the bottom here already feels a little weird. So thinking about this might be the better way for this first problem. I know we've got 50 gallons. I know the rate is 2 gallons per minute. I want to know the time. That makes it clear. Do I divide? Do I multiply? Well, I'm going to divide, but specifically when I go to divide, I know it's natural a lot of us like to do big divided by small, but that's not always the case. We've seen that before. It really have to go with the problem to know if I traveled 4 miles over the course of 35 minutes, it's tempting to say 35 divided by 4, but if I traveled 4 miles over 35 minutes, I would have to do 4 miles divided by 35 minutes to get my rate. So again, it's always like, which way do you divide? It's not just a big divided by small. That happens a lot, but we have to look at each individual problem, make sure the units are working. And this is just like what we were seeing here. Dividing, just to remember, dividing is multiplying by the reciprocal. So if I literally did this, well, 50 divided by 2 is 25. But thinking about the units, gallons dividing by gallons per minute becomes multiplying by minutes per gallon. So that the gallons do cancel, and we are indeed left in terms of minutes. So not the easiest one, but again, following the units or following our formula, there's 2 good ways to guide us. And again, it's not just having the right guidance, it's making sure as we go through, I'm not just trusting the work, I'm testing to make sure the units are doing what they are supposed to. So now I want to go back to this problem in class. So we did the whole setup. We dug a hole, a rectangular hole, because we wanted to do it at a little in-ground hot tub. We had the rectangular base had a length of 6 feet, a width of 4 feet, and a depth of 3 feet. So we did a little problem to find the area first, but then we used all three of these to get the final volume. So I'm just catching us up. That's where we were in class, and this is where I wanted to finish that problem, to extend that. Now that we know the total volume, quick reminder, volume, we do get cubic units, but because, especially when it comes to liquids, we very often use alternatives. So things like gallons and liters and ounces and cups and quarts. But our traditional three-dimensional units, those can still certainly come up as well. So these two problems are incredibly similar. I knew the total volume and I knew the rate we were filling, so we did that total divided by the rate to get the time. That same exact thing happens here. I'm filling my hot tub with my hose, and it's providing water at this rate. I don't say the word rate, but I could just look at the units and I know that is a rate. 8 cubic feet per minute, that's volume over time. That's the idea of a rate. I know the total volume is 72 cubic feet, so the total volume equals the rate times the time. I want how long will it take to fill the hole. I will divide this over, and that is how I will get my time. And same thing here, thinking about the units. Cubic feet divided by 8 cubic feet per minute. I'm doing the arithmetic, 72 divided by 8, and I get 9. That's straightforward. But for the units, just to take a moment to think about the fractions. Feet cubed divided by feet cubed per minute becomes times minute per feet cubed. And there gives us the units we'd expect. If the units here, if the time aspect here was given in minutes, no surprise at all that our final answer in time has those same units minutes. So that's just a good start, just to extend the distance equals rate times time. And here we're talking about filling a bathtub, but think about paychecks. If you make $12, well, actually we're in New York City, so let's say $15 per hour if you make your minimum wage and you work 20 hours, what's your total amount, what's your paycheck? You've got the rate, you've got the time, you get your total. But we could keep flipping that every way. If you make $15 per hour and your paycheck last week was for $200, how many hours did you work? Or, with another flip, if you made $400 in your paycheck last week and you worked 25 hours, what is your hourly rate of pay? So I could still that's all still that same thing, just in another slightly different situation, but still recognizing the idea of a rate. Okay, so now moving on, let's do a little bit of purchasing. They've got a nice example with buying acreage, and then at the bottom here, they do a nice price comparison example. Let's do a fresh one ourselves. Let's do a purchasing problem, and let's focus on gasoline. If gas costs $3.75 a gallon, which just to translate that's $3.75 per gallon, there's a rate. But my rate this time doesn't include time. That's what I was trying to emphasize at the very beginning here. We see a lot of these situations where rates have a component of time, so dollars per hour and gallons per minute and all those other situations. But you realize that still represents a rate. We're getting some aspect of something per something. So we are given a rate. You buy 12 gallons of gas. What's the total cost? Now this is where if you try and go back to this formula, it's like, well, what's the total? I've got 12 gallons of gas, so that's my total, being asked for the total cost. So it almost feels like if I'm thinking about this, well, there is no time, what goes where? So that's why, again, let's try and not just use that formula, but understand the units. You've got $3.75 per gallon. So that's $3.75 per gallon. If I'm looking at the total cost, I need my units here are just going to be dollars. So that means gallons needs to cancel. Well, why would gallons cancel? Gallons in the denominator would cancel if there's gallons. I'm sorry, that's an S, not a G. Gallons, not galling. If I've got gallons here in the denominator, and if I multiply by the 12 gallons, now those gallons will cancel, and my units left behind will be the dollars. And that makes sense. If we're being asked the total cost, how much did we have to pay at the gas pump? Well, we only pay in dollars and cents, of course, but that would be my units. So my units canceled in the right way that they should. Numerically, we'd be left with $3.75 times 12, and it looks like we just spent $45. But now let's reverse that a little bit. We're still looking at gas cost $3.75 a gallon. You spent $20. How much gas did you buy? Well, the gas component here, gas would be measured in gallons. So I see that unit here, and this is one of those situations. It's like, well, how do I end up with gallons now on top? Hopefully with a little more experience, and we can't undervalue experience, everybody. In mathematics and just in life in general, experience is such a big factor. So maybe just from some of these previous problems, that might give you a hint, well, what can I try and do? If I try taking $20 and if I divide by $3.75 per gallon, that feels like the right way to get me started. Whereas if you try doing something else, if you try to just copy this way and go, okay, well, I got $20 times $3.75 per gallon, nothing good happens. Okay, I multiply, but I got dollars times dollars divided by gallons. Nothing good is going on here. So before I do any arithmetic, the units clued me in that I did not have the correct setup. But this time, before I do my arithmetic, thinking about my units, dollars divided by becomes times the reciprocal. So divided by dollars per gallon becomes times gallons per dollar. Now my dollars cancel, and we're left with gallons, which is what we said we should be. So now when we actually do this arithmetic, the gallons are the correct unit, and that's what we're getting, and that supports that that's the work I need to do. 20 divided by 375, so approximately 5.3 gallons, and change, 5.3 gallons. Okay, so purchasing. And again, so many of these situations, we get some sort of a rate. That rate times how much we buy gives us our total cost. If, pants are $25 per pair of pants, you buy 4 pairs of pants, same situation, you'd multiply. And if after the fact, we say, hey, it's $25 per pair of pants, at the end I spend $100, how many pairs of pants did I buy? Same situation that we've got here. Or again, we could do the third situation. If I spent $100 buying 4 pairs of pants, what is the base price per pair of pants? $100 divided by 4 pairs of pants would be $25 per pair of pants. So that's, like I said, you could keep flipping these around, and whether you're buying candy or gasoline or acreage, it doesn't matter. We're going to see a little bit of this as a part of our lab. Even with more complicated units, we're going to look at painting a wall. So if we measure the wall in square feet, we would have to look at how much does it cost to paint per square foot. Or if we're carpeting the floor, carpeting is sold per square foot or per square yard. But all these same purchasing problems are pretty much the same. But now a comparison. We've got 2 options. We want to buy some soda, and we've got 2 options on the store. I can buy a half-liter bottle for $1.25, or I can buy a 2-liter bottle for $2.75. Which is the better deal? This is where the idea of unit price, this is the ultimate way to compare. Let's look at the rate. Let's look at each of these situations and see the rate. In both of these, I'm spending my money in dollars and I'm getting my soda in liters. So let's figure out the unit price in dollars per liter. Now, I will come back and do a quick second point here in just a moment, and this will come up in another example. There's not, some of these comparisons, there might be some nice, clever ways to do some other work to get an alternative solution, but this is a way that will always work, that you don't have to get lucky. And I'll explain what I mean by getting lucky in a moment. So which is the better deal? The unit price will guide me. So in my first situation, I'm spending $1.25 for 1/2 of a liter. Nothing cancels here, so my units are dollars per liter, like we said, and I'm going to do the work. 1/2 is 0.5. If you enter it as 1/2, that works too. I'm sorry, no, I need parentheses. I'm sorry. I would need parentheses just to be clear the order, otherwise it just divides left to right. So that's a little mistake, so just to be careful, either make the 1/2 a fraction or make sure that because that denominator is a little more complicated, just to use your parentheses. So we would be spending 2.5, which would be $2.50 per liter. Now in my second example, 275 divided by 2 liters. I shouldn't say my second example, my second option. So this is option A, that's the base price. Here is option B. I would get 275, divided by 2. I would get 1.375. This is money, so just to round, that would be roughly $1.38 per liter. So now my base price. I had two different monetary amounts, and obviously $1.25 is less than $2.75, but when actually considering how much soda you get, your better price is here. You're getting a lower value for the same amount of soda. $1.38 per 1 liter or $2.50 per 1 liter. Now we've got a fair comparison, and we can see for us, for the store, they'd love you to buy this, but for us, this is the better price. Now, of course, practically speaking, maybe you just don't want that much soda. So why spend the extra money if you don't want it? I mean, of course, when we're purchasing things, it's not always better price. There are a few practicality aspects. Secondly, a lot of situations, the bigger item, you get a better price buying in bulk, but that's not always the case, just sometimes different specials that come up. So a quick follow-up to this problem. Let's think about fast food. I often get, I won't even name a particular restaurant, but I can get 20 chicken nuggets for $5, or there's a special where for $1, I get 6 chicken nuggets. Again, one of those situations, maybe you only want 6 chicken nuggets, so you're just going to spend $1 and that's that. But just thinking about better price, $1 per nugget. This is one of those situations, it's easy. You could do it nuggets per dollar, but most people, we think of our unit price dollars per item. So I'm not picking to do 20 divided by 5 to get dollars per item, dollars per chicken nugget. I'm going to have to do 5 divided by 20. And I would get, that would be 25 cents per chicken nugget. Whereas here, $1 for 6 chicken nuggets would be roughly 17 cents per chicken nugget. So it's not always the bigger one is the better buy. And again, fast food places especially, these little specials and things come up so that this would be the better buy. You're spending less per each individual chicken nugget. But both of these examples have a nice little shortcut. Some people, this works out nicely enough that people can say, well, $5, if I spend 5 of these, if I spend $5 on this price, how many chicken nuggets do I get? So just multiplying this by 5, if I buy in this way for $5, I would get 5 times 6 chicken nuggets. I would get 30 chicken nuggets for $5 here, whereas only getting 20 chicken nuggets for $5 here. So being able to find some way to put these on a level playing field so it's a fair comparison. When I have different numbers of chicken nuggets and different numbers of dollars, that just throws it into an odd comparison. So some way to unify that. Similar here. A half liter of soda, well, there's 4 half liters in a 2-liter bottle. 2 half liters gives me 1 liter, and then another 2 would give me 2 liters. So if I just literally multiply this by 4, I would realize in this option, I would be spending $5 to get 2 total liters of soda, which would again reinforce this was the better deal. So that's where, again, I wanted to point out unit price is a situation that will work in any situation, but sometimes you get lucky that the numbers that you're presented with, there's a way to make them level. I could get the total number of liters the same and compare the price. Or here, I could look at spending the same amount of money and then compare the total number of chicken nuggets that I get to see the better deal. But you don't always get such a perfect situation like that. That if I was getting 2/3 of a liter of soda for $1.25 and 1 liter of soda costs $2, now that's not so easy to get those on the same playing field. Or similarly here, if I was talking about for $2 I get 8 chicken nuggets, well, now nothing goes cleanly. It's not like, well, I get $2 and $4 and $6. I don't get a perfect 5. I would have to work a lot harder to get an even playing field. But the unit price, that worked out very well. So the very last thing here, I do want to point out there's a little in between that I'm skipping over. They do talk a little bit about density. It's interesting. Population density. They do a little blood alcohol problem. They do a quick discussion on units of energy and power. It's interesting, but the last thing I want to do, here's the blood alcohol content example. But the last thing I want to talk about is a little bit of dosage. When you receive medicine, the dosage that goes with your medicine. Now, to be 100% honest, any of these types of situations between your doctor, the nurses, the pharmacist, you get direct instructions on how to take your medicine. Take, 3 pills every 6 hours, or they give it in terms of your milligrams of medication. But it is made completely clear. But let's just take a look at how they do this. So this problem's not bad. I'm sorry, I want to go backwards for 1 second, everybody. I wanted to point out in this example, this was another one of those problems, a little comparison. Not just unit price, but just thinking, you're 90 miles away from your destination, your gas tank is 1/4 full. The whole tank holds 12 gallons of gas, you average 25 miles per gallon. Do you need to stop for gas? Several ways to do this. What they do is they figure out the miles you have left and the miles per gallon. They figure out how many total gallons of gasoline you need to finish your trip. And then they go, okay, you've got 1/4 of a tank, 1/4 of a 12-gallon tank. You need 3.6 gallons of gasoline. You only have 3 gallons of gas right now. You need to stop for gas. But another nice alternative, your tank holds 12 gallons of gas. You've got 1/4 of a tank. So again, that leads to you have 3 gallons of gas. If you average 25 miles per gallon, we can figure out by just multiplying here, you are only going to be able to travel 75 total miles with your remaining gas. You've got to travel 90 miles. So again, similar to the unit price, there are sometimes some alternatives to just think about and to come up to a good decision. How much gas you need, how much gas you have, you don't have enough. Or my way here, how many miles you can travel with the gas you have, how many miles you have left to go, you're not going to make it. You need to stop for gas. Either way, we're making the same conclusion, and we have good supporting evidence to show how we reach that conclusion. So last idea, like I said, dosages. Doctor prescribes a medicine that calls for 3 milligrams of medicine per 1 pound of body weight. That is a rate. 3 milligrams per 1 pound. If you weigh 145 pounds, how much medicine should you take? We've got a rate. Per pound, my weight is given in pounds. So again, focusing on the units. Milligrams of medicine per 1 pound. How much medicine should you take? My answer is going to come out in milligrams. So if I've got pounds in the denominator here, pounds are my weight. If I multiply, my pounds cancel. Oh, I apologize. I used the abbreviation here. I did mention in class, you don't have to remember the abbreviations. You could certainly write it out, pounds. That cancels. We'll do the arithmetic. We should take 435 milligrams of medicine. But then a follow-up question. You're supposed to take this medicine 3 times per day. Times per day, how much should you take each time? Well, we're taking all of this in 1 day. So if we take the 435 milligrams, divide by the 3 times per day. Now when I divide, I would be taking 145 milligrams per time. And like I said, everybody, this would be a situation where, again, your pharmacist would have this worked out and they'd have it. So, okay, each pill is like maybe 145 milligrams. So you take 1 pill 3 times per day. 1 pill every 8 hours, that type of situation. But all of this, even when it gets to medicine, still all the same types of situation. Being able to identify a rate, we could reverse these problems. If I told you, you weigh 145 pounds and are being told to take 435 milligrams, what is the dosage per pound? We take the 435 milligrams, divide by the 145 pounds, and we would end up with this dosage rate. And then maybe we could figure out how much somebody else should take. If we knew this information, we can get to this, and we say, okay, well, my next person weighs 210 pounds. They're going to take more medicine, but how much more? We do a similar type of computation. So that's it. 2B. Not a bad section, but you could see how things have extended. A lot of it is just still getting very comfortable working with units. We got some comfort in the beginning, saw some ability to convert, how units work with each other in 2A, and now in 2B, just that extension, not just making conversions, being able to see some units in a problem, being able to see the units being presented, and then being able to use those and work towards a solution that makes sense. And that's the biggest thing, everybody, at the end. We do a lot of examples that, do kind of make sense in the everyday of things. I try to use some, this is a dosage that makes sense. That sounds like a reasonable amount. If you follow dosages, that is, some places gas is already a lot higher than that, but I'm trying to do some reasonable values. But even if you don't have experience with these quantities, with these situations, that, again, having good experience with the units, as we keep saying, I'm not just doing random arithmetic and assuming the unit that I want is there at the end. I'm verifying it through my arithmetic, making sure the units interact the way that they should. Okay, everybody, so like I said, that's it for this week. We have spring break next week, a great opportunity to really get some extra practice with Chapter 2, to knock out one, if not two homeworks, to get you closer, if not finishing your homework for the entire semester. Get some good practice. When I see you on Monday the 25th in person, a lot of review. I did mention we are going to do a lab, introduce a lab that day, but that lab is going to tie in with all this and just do more review work so that the Monday after that would be an in-person test on this type material. Okay, everybody, enjoy the break, enjoy the holidays, and I'll see you all when we get back.